Okay, that's 9:43 a.m. Pacific Standard Daylight Saving Times. This is Physics 7. And let's share the screen here. Okay, so we are writing here the 24th. We had an exam last Wednesday. Today is Monday, 24. And let's continue with chapter 21, which is magnetic forces and fields, right? And move it aside. Let's see. Just to make sure, can you see my notes here? I'm scrolling up and down. Can you please confirm that you can see it? That's okay, good. So that's good to know. Insert page break. Today is March 24, 25, Monday, and this is week number 7. Week number 7. Number 7, right? What the last thing we saw? Okay, we're just talking about the very basics of the magnetic field. The magnetic field and magnetic force. That's, just the very beginning, right? And let's get this student in here. So we just started covering the magnetic field. The difficulty of electricity and magnetism is that because we are dealing with invisible concepts, and so that's the main challenge of this course, okay? And the way that we figure out how to make the invisible visible is by using those mathematical tools that we have, like the vectors, right? That's the way we figure out how to make it visible, the invisible visible, by using the mathematical tools and drawing the mathematical tools in the paper. Not just in the paper, but also in the documents that we type, right? Okay, so look how things are going on here, right? Let me just do a quick review how this whole course is progressing, right? Quick review of how this course is progressing. First, I told you about the electric charge, a property of matter. Okay, we need, that's the basic quantity, a basic quantity, property of matter, and a basic quantity. A basic quantity of matter. Let's put it this way, that's better. A basic quantity of matter. And then you must use your imagination to picture those electric charges in the matter. Okay? So then why do we do that? Because the electric charge, the concept, the idea of electric charge is used to explain the electric force, which is observed, which is observed in nature, right? It's observed in nature. And the idea of electric force is used to explain an invisible quantity that we call the electric field. Electric field. The electric field, here you go. The electric field, which is the electric counterpart of the acceleration of gravity, can be represented by a mathematical tool called the vector, right? An arrow, a vector or arrow. Okay, this arrow is used to visualize. Visualize something that is invisible. And it's a very useful way of seeing what is invisible. Next to the electric field, let's say we have electric charge, we have the electric force, electric field, and we have the electric potential, right? I'm going to skip the electric potential here, electric potential energy, electric potential, until we come to something else that's very important too. Something else that is so important that some people refer it as the real basic quantity of matter. Okay? Many books, instead of making reference to the electric charge as a basic quantity of matter, many books refers to the electric current as a basic quantity of matter. And there's a reason for that. There is a reason for that. The reason for that is that it's much easier to measure an electric current than to measure an electric charge, okay? Electric current is also a very important concept, so important that some books refer it to being the real, refer it to being the basic quantity of matter instead of the electric charge, okay? Instead of the electric charge. And then there's something else important about the electric current. Something else very important about it. Something else very important about the electric current. It is the actual source of the magnetic field. Okay? Electric charge is the source of the electric field, right? Electric current, I'm going to copy and paste it. It's almost the same phrase, right? Is the source of the magnetic field. Can you remember that? Those are very important concepts to memorize, to keep it in mind. And those are very good ideas to understand the invisible universe. Okay? Is the source of the magnetic fields. Okay. And just like the electric field, we represent the magnetic field as a arrow, as a vector. just like the E field, comma, we represent the B field as a vector or arrow. Okay. More students coming in. Let me get my illustrations here. Magnetic fields. Here you go. Okay. So the magnetic field has a positive and negative charge. Okay. But charge, between poles. It's not exactly a charge. We call it poles. And unlike the electric field, we cannot separate the positive from the negative. Right? So here you go. Let's write that down again. The magnetic field that have a positive north and negative south polarity. Let's put that for charge, right? Just like the electric field. However, unlike the electric field, you cannot separate these two poles or charge, okay? Unlike that's a very important distinction between magnetic field and electric field. And then we have, we can start talking about the mathematical laws of electricity and magnetism. Mathematical laws of electricity and magnetism. Okay, because we can separate a positive electric charge from a negative electric charge. Okay, we have this law of physics, Coulomb's law, written in a different way, that states that the flux of the electric field is equal to the charge enclosed by an imaginary surface divided by this constant epsilon naught, okay? Now, because there is no isolated magnetic pole, because we cannot separate a positive pole from a negative pole, this equation that you see, the corresponding equation for the magnetic field is going to be different. It's slightly different, okay? So, and what's the difference here? Here you go. We still have a magnetic flux, but because we cannot separate one pole from the other, any surface encompassing the source of the magnetic field is going to be, the right side of this equation is going to be equal to 0. Can you remember that? Okay, that's one of the laws of electricity and magnetism. So let's, okay, so laws of electricity and magnetism. The first law that you saw was this one here, Gauss's Coulomb's law in a different format. Okay, Coulomb's law. Coulomb's law for electricity. And then we have Coulomb's, let's say, we actually call that Gauss's law. In this format, we call it Gauss's law for electricity, okay? And then we have also the Gauss's law Gauss's law for magnetism. Here we change it from E to D. And what ends up on the right side is going to be the number 0. Just like Newton's laws of motion, those are also laws of physics. And I like to tell my students, you have to memorize the laws of physics for the rest of your lives. Okay? Now, characteristics of the magnetic field. Characteristics of the electric and magnetic fields. Okay? Source. You know, the source of the electric field is a positive charge. Is the positive charge, right? Not a, but the positive charge. The sink of an electric field is the negative charge. And we have the same thing for the source and sink of the magnetic field. North pole of a magnet and the sink of a magnetic field is the south pole. Another parallel between them, right? Differences, let's see. And what is another law of magnetic field, right? So here you go. I'm going to write now another law of electricity and magnetism. Electricity and magnetism. You know, I'm not going to write that down in mathematical format, but I have already mentioned before the actual source of the magnetic field, okay, is not the positive pole. It's not the positive pole, okay? Not the positive pole. Only it's actual there. If you go into the microscopic nature of matter, the actual source of magnetic field is the electric current. Okay? It's the electric. Remember that we didn't made a statement, a mathematical statement about that yet. Okay, but we're going to make it very soon. And we have a fourth law of electricity and magnetism, fourth law of electricity and magnetism that we will discuss later on. So those are the 4 basic ideas that you have to keep in mind. Okay, the very foundation of physics. We didn't get to the 4th law yet, but I will show that to you very soon. Okay? And let's take a look at the drawings here. North Pole and South Pole. Okay, here you go. You cannot divide. Here you go. Again, this is a law of physics. You cannot break up a magnetic pole to separate the north from the south. It's impossible to do that. Every time that you break a magnet, you know, you're going to form the 2 poles all over again. Like something like that doesn't happen. Something like that happens. And here you go. That's how the magnetic field of a magnet, we call that a dipole, magnetic dipole. That's how it looks like. If you put a compass needle nearby it, you're going to see that the needle is going to behave like that. The needle is going to point tangent to the magnetic field lines. Okay? Here, the center of this compass is pointing tangent. It's positioned tangent to the magnetic field lines. And it is the north pole of the magnetic needle, the north pole of the magnetic needle points towards the south pole of the magnet. And the reverse is also true. Okay, let's write it down. No? The magnetized needle of the compass points tangent to the magnetic field line of a let's say of a bar magnet. That's what the drawing shows. And the Earth behaves like a magnet, like a giant magnet. Here you go. Here's the Earth. The Earth rotates about its axis. The point where the rotation axis of the Earth intersect with the surface of the Earth is the north and south geographic pole, right? So that's here you go. The Earth behaves like a giant magnet. Okay. We do know that the Earth rotates about an imaginary axis of rotation. Okay. Okay, this is a mechanical idea of the Earth. Okay. The point where the axis, the imaginary axis, crosses with the Earth, the 2 points, right? The 2 points where the imaginary axis or the imaginary axis of rotation, right? Axis of rotation intercept, not cross, but intersects with the Earth's surface, are the north and south, you go, geographic poles, okay? Remember that? North geographic pole, south geographic pole, respectively. NGP and SGP, respectively. Okay? On the top, in addition to that, in addition to the axis of rotation, comma, the Earth also have a magnetic axis that makes a very small angle with the Earth, with the axis of rotation of the Earth. Can you picture that too? It's you know, it's on the order of 10 degrees, right? Let's take a look at the internet. And the position, here you go. Angle between the axis of rotation and of the Earth, and its magnetic axis. Let's see, what's the angle between them? Yeah, see, 10 degrees, around 10 degrees, 11.3 to be more precise. Okay? And because this angle is so small, Because this angle is so small, but so small, we can use compasses to find out where more or less the direction of the North Pole is located because of this small angle, okay? There are planets out there in the solar system. You may already know that, right? Like Uranus. It has the tilt of its magnetic axis and its rotational axis is huge. It's like 90 degrees. Okay, it's 90 degrees. It's amazing that we have this type of situation in the solar system. Okay. In addition to the axis of rotation, the Earth also has a magnetic axis that makes a very small angle with the axis of rotation of Earth. You know, 11. Well, let's see, 11 point what? 11.3 degrees. 11.3 degrees, or roughly. It's easier to memorize 10 degrees, right? If you say that's 10 degrees, you are incurring only in a 10% error. And here you go. Here's the illustration. North geographic pole, south geographic pole. But there is one more important thing. Here you go. Here is the magnetic axis of the Earth. This angle is around 11 degrees, right? And there is one more important thing. At this very moment, the south magnetic pole is closer to the north geographic pole, and vice versa. And the north magnetic pole is closer to the south geographic pole, okay? For this reason that the north pole of your needle, of your compass needle, points to a place that's closer to the north geographic pole, okay? And here you go. And every now and then this polarity changes, okay? Every now and then this polarity of the axis of the Earth changes. We have evidence, archaeological evidence, that shows something that happened every 100,000 years. Let's take a look, the exact amount of time. Flipping, right, of the magnetic poles. Let's see. Oh, it's 450,000 years, not 100,000, 450,000, roughly, okay? Though it's a chaotic and unpredictable process. Geomagnetical reversal. It looks like we are overdue, right? Okay, yeah, we are overdue. See that? Geomagnetic reversal is statistically random, with the last one occurring around 780,000 years ago. So we are overdue. So at this very moment, we may have a reversal of the magnetic field of the Earth occurring. We may have. Reversals are not instantaneous. They happen over a period of hundreds of thousands of years. What causes them? They don't know exactly what causes them, but the forces that generate our magnetic field are constantly changing, causing the field itself to be in continual flux, its strength waxing and waning over time. People believe that has to do with the flow of current in the core of the Earth. Okay, so what else? In addition to the axis of rotation, the Earth also have a magnetic axis that makes a very small angle with the axis of rotation of the Earth. Okay, the south magnetic pole. I think I already wrote that, right? Doesn't look like, okay. Doesn't look like I did. Okay, the south magnetic pole is closer to the north geographic pole, and the north and vice versa. The north magnetic pole is closer to the south geographic pole. So don't forget when you're getting when you get your compass, that compass is pointing to a point that's close to the north geographic pole. But this point that the magnetic compass is pointing to is the south magnetic pole. We have this reversal at this point in time, at this point in the geological time of the Earth. Okay, so here you go. And here's the magnetic axis. Right, here you go. That's another way of illustrating this magnetic axis, where I'm now illustrating the geographic pole with respect to the magnetic pole, right? And here you go. Here is the magnetic field line of the Earth. Magnetic force, right? Negative pole, like poles repel each other, and like poles attract each other. That's another one. You go, like poles repel each other, unlike poles attract each other. Just like positive charges attract negative charges and vice versa, right? And then we can start talking about the magnetic force in a moving charge. That's gonna be the new thing here that you have to know. Let's take a look at the book. Wiley plus, let's go to Wiley plus here. Log in. Log in. P07. Force resources. Launch. We're working chapter 21. Magnetic fields, the force that magnetic field exerts on a moving charge. Okay, that's what we're going to cover now. And let me close this one here. Word, close it. I need this one here. And I want to go magnetic field, magnetic force on a moving charge. Okay. And what else do you observe? Okay. In addition to the force between poles, we also, okay, the magnetic force, in addition to the magnetic force between poles, we also have a magnetic force exerted in a moving electric charge. But it's not every type of moving charge, but it is not every type of moving electric charge. Okay, now you're gonna see the difference here. Okay, very important. Okay, here you go. If a charge is at rest, what do we observe experimentally? Okay, we can consider that a law of physics as well. I'll say the fifth law of physics. If an electric charge is at rest in a magnetic field, the magnetic force is zero. Okay? Remember, can you remember that? Okay, so magnetic force applied to a moving charge. Magnetic force applied to a moving charge. If a charge is at rest in a magnetic field, comma, the magnetic force is zero. Okay? One more situation. If the charge is moving parallel to the magnetic field lines, the magnetic force is also zero. Okay? If a charge is moving, if the velocity vector of a electric, I'm talking about an electric charge, okay? An electric charge. An electric charge. So an electric charge. So let's put here, moving electric charge. An electric charge that rests in a magnetic field, the magnetic force is zero. If the velocity vector of an electric charge is parallel to the magnetic field, the magnetic force is also zero. It's also zero. Okay? And we can observe that in the lab. It's not difficult to show that. Okay? Now, the next one, what if the motion of the charge is perpendicular, the velocity vector of the charge is perpendicular to the magnetic field lines, okay? Okay, so if the velocity vector of an electric charge is perpendicular to the magnetic field, I should put the magnetic field lines, right? Perpendicular, that's rest. Let's see. It's parallel to the magnetic field lines, right? The magnetic force is given by QVB. Can you remember that? QVB. And I'm going to write that down. F of B equal to like that. And there is more. It's not just that. You gotta know too the direction of the magnetic force. The magnitude of the magnetic force is given by that. If the velocity vector, the magnitude of the magnetic force, is given by that. And its direction is given by the right hand rule. Okay? The right hand rule. And how is the right hand rule applied? Oh, you get your right hand. There are several ways of using the right hand, right? The right hand rule. The one that I like the most is, let's say a charge is moving, the velocity vector, let's put it right here. Here you go. Here's the velocity vector of the charge, right? So if you lay the palm of your hand along the direction of your right hand along the direction of the velocity vector and cross it towards the magnetic field, the thumb is going to point in the direction of the force. Okay? Direction of the force. That's one way of doing that. Your book has a similar way. It has a slightly different way, but gives the same result. Okay? Let's take a look at the book. I like this one because most books gives this rule, V towards B. Okay, that's why I have here this cross sign. This cross sign means that it tells you the direction of those two vectors. This is the vectorial multiplication sign. V towards B. And the direction of the thumb indicates the direction of the force, okay? The right hand rule, okay? How does the right hand rule works? Lay a point, the palm of your right hand towards the direction, the vector velocity direct towards the direction of the vector velocity, the direction of the vector velocity. It has to be the right hand. Don't use the left hand, right? And rotate it towards the direction of the magnetic field vector. Your thumb will point your thumb will coincide with the direction of the magnetic force. Okay, that's one way of using the right hand rule. That's the way I like the most. Let's take a look at let's see, magnetic fields. Go moving charge, right? So here you go. Oh, here's another way that your book uses the right hand rule. The thumb in the direction. This way is nice because it doesn't require any motion of your hand, okay? So you lay down the palm of your right hand. Let's see, the palm points towards the B field and the thumb points towards the V velocity vector. And the force is going to be perpendicular to the palm of your hand. That's another way of using the right hand rule. The final results should be the same. The final results should be the same. Okay? And then one more. Well, I don't have everything. I'm gonna have everything now, okay? If the velocity is perpendicular now, if the velocity vector of the electric charge makes an angle theta with the magnetic field, huh? Symbol. The magnitude of the magnetic force is given by sine of theta. All of that that you saw there, multiply it by sine of theta, right? And this direction is still given by the right hand rule. And its direction is still given by the right hand rule. Like that. This one here is the most generic equation. Mathematically speaking, here you go. Mathematically speaking, the magnetic force is given by the following equation. Let's get my Chico. Following equation, here goes magnetic force Q V B sine of theta. Okay? 1, 2, 3, where theta is the angle between, angle between the velocity and magnetic field vectors. Okay, and this angle is given whenever the two vectors are putting tail to tail. Magnetic field vectors whenever they are placed tail to tail. Okay, that's how you measure the angle between vectors. That would be the next slide. Okay, here you go. See the velocity vector right in here? That's the velocity vector, right? That's the velocity vector. I'm gonna copy and paste it. I'm going to take this one out so you don't confuse, right? The angle theta between the velocity vector and the magnetic field vector is given by placing the tail of both vectors together. That's gonna be by angle theta. Applying the right-hand rule, the direction of the force is still gonna be perpendicular, simultaneously perpendicular to the magnetic field and the velocity vectors. Okay, the direction of the force, of the magnetic force, must be, right? Applying the right-hand rule, here you go. Applying the right-hand rule, comma, the direction of the mathematical force, the direction of the magnetic force ends up being simultaneously perpendicular to the velocity and magnetic field vectors. Like that. Okay, so here you go. Here's the force. You know, this dot here, this point means that the magnetic force is pointing away from the plane of my screen. Okay, that's what this point means. So this direction is going to be perpendicular to the magnetic field vector and also perpendicular to the velocity vector. So that is the most generic force. That's the most generic equation for the magnetic force. Now, and then you can double check that. If theta is equal to 0, right? The magnetic force is equal to 0. If the velocity is equal to 0, the magnetic force is equal to 0. If theta is equal to 90 degrees, the magnetic force is going to be QVB. See that? And then, you know, this equation applies to every possible configuration, every possible values of the velocity, magnetic field, and angles. Okay, and don't forget, if the charge ends up being negative, right, you gotta invert the direction of the force, right? Here we are doing for Q greater than 0. Okay, here in this case, Q is greater than 0. Here you go. If Q is less than 0, then this direction inverts, okay? Now I'm gonna put another slide here. If Q is less than 0, right, now this dot here is replaced by a, let's see, we have it here, this one right in here that I want, by a cross. And the cross is just the back of your vector velocity. The tail, right? We're looking at the tail of the vector velocity. No field. Let's shrink it a little bit. Direction. That's how we represent the vector, the direction of the vector, of the force vector. Okay, if Q less than 0, Q greater than 0, okay? Let me do it in a better way here. Let's see if I can get it. I want to give you the illusion, right? That only the vector is changing. Yeah, okay. And now I'm going to do what? I'm going to send to the back. Oops. Send to the back. Ooh. Didn't go to the back yet. Send to the back. Why it doesn't do it? Okay, now I can do it. This one. Yeah. Now I got it the way I want. Here you go. See that? We have to change this sign. Have to change the sign here. Right, here you go. Now you got it right. And now I don't need that anymore. Okay, so here you go. B vector, another example. Okay, that's the direction of the force. What about this one? V greater than 1. Oh yeah, force provided Q less than 0, Q greater than 0, Q less than 0. Okay, here you go. Same thing here. If Q is greater than 0, then the vector force should be coming out to away from the spring, right? If the charge is negative, it's towards the spring. Towards the spring. Okay. And then what does it mean for the motion of the charge, right? How does this force affect the motion of the charge? The question, that's the next question you have to make. How does this force affect the motion of the charge? That's something that we're going to talk after the break. Okay, I want to take attendance right now. The roster must be here. Okay. Lab lecture. Today is the 24th. That's good. Let's see when's our exam, right? Next exam. Let's see. Gonna be 16. How many weeks do we have there? 1, 2. It's going to be 3 weeks and a half. In 3 weeks and a half, we're gonna have our second exam. And before the exam, we're going to have all those holidays, right? Cesar Chavez days and the spring break. So it's kind of far away, too far away. And let's go get there. Any questions about this material? Okay, so here you go. Abir Ahmad, are you there? Hello, Abir. I can see Abir's here, but must be away from the computer. Are you? I cannot hear you.
Hello?
Okay, now I can hear you. Okay, good. So, thank you. Nestor Alvarado. Is Nestor here? I don't see Nestor here. Monte. Hello, Monte.
Here.
Thank you.
I'm here.
Thank you. Thank you. Hasti Amin.
Yes, Professor, here.
Thank you. Isabel. Isabella, right? Not Isabel, Isabella. Okay. I can see Isabella here, but I cannot hear her.
Here.
Okay, thank you. Justus Bowden. I can see that Justice is using my roster, Zoom roster, but I cannot hear him. Oh, yeah, thank you. Alexandra Bormistrova.
I'm here.
Thank you, Alexandra. Benjamin Carvajal. Thank you, Benjamin. Brianna Carrillo. I don't see Brianna, right? Okay, looks like Brianna. Is that Elizabeth Castellano?
Here.
Thank you, Elizabeth. Natalia Córdoba. Hello, Natalia. Are you there?
Hi, I'm here.
Okay, thank you. Next is Jacqueline Delgadillo. I don't see Jacqueline here. Next is Jenny Diaz.
Here.
Thank you, Jenny. Valerie.
Here.
Thank you, Valerie. Juan Escalera. I don't see Juan here.
I'm here.
Oh, you're there? Okay, thank you. Bianca? Is Bianca here? Let's see. Doesn't look like Bianca is here, right? So, Galia. Thank you, Galia. Edwin Gonzalez. Thank you, Edwin. Ellie Gonzalez.
Here, Professor.
Thank you, Ellie. Manuel Hernandez.
Here, Professor.
Thank you. Samantha Hubert. Samantha here. I don't see Samantha here. CJ. Let's see. CJ is here. No, I don't see CJ. Luis Leal. Are you there, Luis? No. Amber Lopez. I don't see Amber. Arely Lopez. Doesn't look like Arely is here either. Genesis Lopez.
Here.
Thank you, Genesis. Mary.
Here.
Thank you. Ramon Olivares.
Here.
Thank you. Taylor Forn. Forn is here. No, I don't see Taylor here. Jeremy Pittman. Jeremy, I don't see Jeremy. Huh? Jeremy doesn't seem to be here. Okay. Stephanie Ramos. Thank you, Stephanie. Leslie Rios.
Here.
Thank you. Jason Strait.
Here.
Thank you. Hema Torres.
I'm here.
Okay, so let's see how many students we have. 23. Yeah. Was everybody called? Looks like there's one student here who didn't answer my call, my roll call.
It was probably me, Professor. My Wi-Fi was acting up.
Okay, who is that? Nestor, right?
Nest-
Okay.
Yeah.
Okay. Thank you. Thank you. 24. Now we have 24. Okay, so go back to our and that break. We're going for the 10:43 a.m. to let's see 10:58, right? 58 a.m. So I see you in 15 minutes. See you then. Bye-bye. Stop sharing. Okay, I am back here. So the next thing that we're going to do is how does the magnetic force affect the motion, right? How does magnetic force affect the motion of the charge? Okay, what type of motion we're going to find, we're going to get when we have this type of a force that's perpendicular. By the way, the force is perpendicular to the velocity vector, okay? And it's very important. Okay, but let's see. How does magnetic force affect the motion of the electric charge? Okay, what we are going to do? We are going to investigate the motion of the charge for the case of a uniform magnetic field. Okay, uniform magnetic field is easier. It's easier to treat that. If the magnetic field is, changes in magnitude and direction, then it becomes more difficult to analyze the motion of the charge. So we're going to look at the simplest case of motion, which is a uniform magnetic field. Uniform magnetic field is represented just like that, right? The lines of magnetic field are evenly spaced, and we can start thinking how the motion of the charge is going to end up being. Okay, even not only if the magnetic field lines are evenly spaced, what does it mean? It means that the magnetic field is pointing just a single direction, and also the magnitude of the magnetic field is the same throughout this space. Okay, it's possible to produce a uniform magnetic field, and we're going to see later on, okay, how we can produce a magnetic field, a uniform magnetic field. Okay, it is, so let's write it down. It is, in practice, it is possible. In practice, it is possible to generate a uniform B field. Yeah, it is possible. That it's possible to generate a uniform, and we will see how to do that later on, later in the course. Okay. Okay, so if the B field is uniform, the force will, the magnitude of the force will be constant, given by, we're going to investigate the motion of the charge for the case of uniform magnetic field and each other case. And the perpendicular, not just uniform magnetic field, but the perpendicular to B, okay? And then later on, we are going to see how the particle moves if B is not perpendicular to B, okay? If B is uniform and B is perpendicular to B, the magnitude of the force will be constant. Okay. Constant and given by, here we go, QVB only. Okay. Now, note that the force is perpendicular to the velocity vector. Right? Just like you saw before. Let's go back. Let's go to our, okay, right in here. Okay, so here you go. Now we're looking at this situation here through a different angle so you can see more clearly where the car, how the particle is going to move. Okay, so instead of looking with at this angle, okay, we're going to look from the top of this drawing. Okay, and from the top of this drawing, the magnetic field is going to look like the following. And let me, before I do something like that, let's see here. Okay, so here you go. Now we are looking into the magnetic field lines. The magnetic field lines are coming out of the plane of my screen. And we can go ahead, play the movie like I always like to do. Here you go. Right? And I'm going to start removing some of the B perpendicular to B, right? Each of those dots that you see here means the magnetic field. And here you go, we have, I'm gonna make as simple as a drawing as I can. I don't need that, right? Here you go. What else? I'm going to remove the charge. And then we're gonna play the movie. I don't need this one here. All right, and we're going to start with the magnetic field. I'm gonna remove this guy and play the movie for you. Okay, we start with the magnetic field lines. One more, right? Let's do one more. Here you go. We start with the magnetic field lines, with the uniform magnetic field lines. And I'm gonna label them. After label them, I'm gonna put my X and Z axis. The Y axis is pointing in the same direction as the B vector. Okay, I'm gonna put my electric charge here. It's a positive electric charge in this case, and I am going to show the velocity vector. In this case, the velocity vector is perpendicular to the magnetic field lines. You gotta do the V cross B right-hand rule, right? When you do the V cross B, okay, V perpendicular to B, V cross B, you get this type of force. Magnetic force is perpendicular to the velocity vector. And every time that we get a force perpendicular to the velocity vector, we are going to get what type of motion? We're going to get a circular motion. Remember that? Okay? Especially if the magnitude of the force is constant. So that's going to be the type of motion that we are going to get for the charge. Here you go. Okay? The velocity, because the force is perpendicular to the velocity doesn't change its magnitude. It changes only its direction. Okay? And we can go with another illustration here to, let's, yeah, okay. Let's move this guy to another place right here. I don't need this. This one is not supposed to be here. The velocity vector is going to change direction, and so is the magnetic field vector. Here we go. The magnetic field vector up. Label. Magnetic field vector is going to change direction as well. Right? My Q moves as well. Here you go. Let's see how the animation becomes, right? Here you go. This position, this position, this position, right? just gonna move in circle. And that's the type of thing that we can observe in real life. We do observe that in real life. In the lab, we have devices that can show that. Okay? Do you see how we get to that? Right? Now notice that the force is perpendicular to the velocity vector because F, because of this, the magnitude, the speed, right, of the particle does not change. Only the direction of the velocity vector. Only the direction of the velocity vector. Also, the particle undergoes uniform circular motion. Okay? Okay, so well, characteristics of the motion, right? Characteristics of the motion. No? Let's see. Uniform force. Magnitude of force. No, not uniform force. Magnitude of the force is constant. Okay, 2, velocity vector perpendicular to force vector. To force vector. Okay. Because of the I'm gonna put it once we go. Let's do it this way. Numbers. 1, magnitude of the force is constant. 2, velocity vector perpendicular to the force vector. Right? Because of 2 and 1, because of 1 and 2, right? 1 and 2. No, wait a minute. Yeah, because of 1 and 2, comma, the speed of the particle does not change. Of the particle does not change. 4, however, the direction of the velocity vector does change. Okay. 5, particle undergoes uniform circular motion. Particle undergoes undergoes uniform circular motion, UCM. And we can play a little bit with that, you know. So let's say we can, for instance, find the radius of this circle. Let's do that. No, example. Find a given Q, B, given Q, V, and B, right? Find the radius of the circle described by the particle. Okay? We can solve this simple example. We already know V perpendicular given Q, V, and B, and the fact that V is perpendicular to B. Find the radius of the circle described by the particle. Okay? Because, and what else I have to tell you? I also have to tell you the magnetic, assume the magnetic force is the only one. Assume the magnetic force is the only force, is the only force acting on the particle. Okay? Because the motion is UCM, right? We have that the magnetic force, the B force, is a centripetal force, right? You see that? Oh, we need one more thing here. Given m, we need also the mass of that particle. Otherwise, we cannot solve this problem. Given m of the particle, mass of the particle, charge of the particle, velocity of the particle, and b, and the fact that v is perpendicular to b, find the radius of the circle described by the particle. Right? So here we go. Because the uniform is uniform circular force, you know, this magnetic force is going to be equal to the centripetal force, which is given by mv squared over r. Okay? We know m, we know v, we know q, we know b. The only thing that we do not know is r. And now we can solve this equation to find the r. Okay, v is going to cancel out with v. We can solve for r. R, QB goes to the other side, and that's the radius of the circular motion of the particle. Of the circle described by the motion of the particles. Okay. And then you can also come up and say, look, we can come up with another example. Another example. Find the period, find the, referring to the previous problem, referring to the previous problem, find the period of motion of a full circle. Okay? How long it takes for the particle to complete a full circle. Solution? Okay. Because the uniform circle, because the motion is UCM, right? We can write the following equation, okay? Because, you know, a full circumference, 2 pi r, right? Divided by a given amount of time that I'm going to call t, and this given amount of time t is the period of motion because it corresponds to a full circle, must be equal to what? Must be equal to the speed of the particle. Okay? I'm going to highlight what I don't know. I do not know this guy here. And we can here write our period. You go in the right side. I don't need that. And I can do one more thing here. I can replace R. I can replace R with the previous equation that we got right in here. Here you go. Right? V cancel out with V. QB can go downstairs. And that is going to be the period of a single rotation. Like that. Eleven 20. Okay. Let's take a look at, and by the way, this type of motion can be used to explain the auroras we see nearby the north and south geographic poles of Earth. Yeah. And there is even a video. Let's see if I can get a video for you. One way to visualize this type of motion, one way to visualize this type of motion is to use the Crookes tube. Okay? The Crookes tube was the predecessor of the cathode ray tube, CRT, which was used in the old TV and computer screens. Okay? Today, this is 100-year-old technology. The CRT is a 100 years old technology that was recently replaced by the LCD, LED, and by the LCD, LED, and OLED screens, okay? It was starting in the year 2000, that the CRT TV screens were replaced by this simpler technology that's much thinner, right, and lighter. Remember, anybody knows? Have anybody seen the CRT before? A TV with a CRT cathode ray tube before? That's big fat TV screen. Let me see if I can show you up. I don't think so. Okay, Amber doesn't. Okay, let me see. Maybe your grandmother may have those TVs. If you go to those electronic shops that people store those old stuff, you're going to see a monster, a big monster, and a screen. Okay, let's see, CRT TV screen, cathode ray tube. Okay, here you go. Here go the old TVs, right? It doesn't show the back, unfortunately. Let's see. Okay, let's see. Here, okay. See that's the screen where the image is seen, okay? But that's the back of the screen. What you have here is the CRT, the cathode ray tube. Older TVs and older computer screens use this technology. my old computer that I bought, my old Macintosh my first computer that I bought, used one of those. Okay, here you go. That's a better picture, right? See how thick they are? Okay, another one, Triniton CRT computer monitor. TV screens were like that as well. They were not thin, and they were heavy and bulky. We finally come up with this. Oh, here you go, the CRT again. But think about that. It was kind of a revolutionary this invention. Even though we have something much simpler, lighter, and thinner, it was still very revolutionary. We used that for 100 years. Okay, here you go. Monochrome CRT as seen inside a Macintosh Plus computer. Okay. Here you go. Monochrome CRT, 90-degree deflection, blah, blah, blah. Okay. And everything started with the Crookes tube. Crookes tube. Let's see. We have a Crookes tube simulation. Let me see. Crookes tube. Let's take a look at this one here. Let's see if this is a good one. How it works, how the Crookes tube works. Okay, we have one of those there at LA Harbor. I like to show that to my students when I do my in-person class, okay? So we have this cross, they put that on purpose. So you can see the image that's going to be formed right in here. The electrons are emitted from this little plate, okay? And let's watch the movie first. Here you go. History Museum, see that? Crookes tube is an experimental apparatus invented during the second half of 19th century, 1850, right? To demonstrate the emission of cathode rays. What's a cathode rays? Cathode rays are streams of electrons, several electrons coming out in a vacuum tubes, inside vacuum tubes, okay? And we can use the Crookes tube to visualize also the path of the electrons, okay? That path, the circular path that the electrons take whenever you subject it to a uniform magnetic field. We can do that. It's possible to do that. Now, here you go. We're going to apply. Okay, this is an illustration of what happens, okay? How does it work? This little piece here is emitting electrons, thermal electrons, by applying a high voltage between those two ends that you see right here, okay? Positive and negative. And what this cross is doing here? This cross is doing here for a very simple reason. If we remove this cross, this tube here is coated with a material, with a powdery substance that emits light whenever the electrons collide against them, the phosphorescent material, okay? So that's what this guy does. When you apply a high voltage between those two ends, electrons are accelerated between those two ends because of the electric potential difference, and they collide against the inside of this tube that has that phosphorescent substance that produces a luminescence when the electron collides, okay? That's how it works. Electron collide with this phosphoric material, makes the phosphoric material emit some light, greenish light. The glass tube contains, you can also put gas at a very low pressure. When electricity is applied to the electrodes, the cathode emits a stream of the electrons, which are invisible to the naked eye, okay? But make the gas luminesce when they strike it. The glass luminesce, right? Glass tube contains gas, a very low, an obstacle in the shape of a Maltese cross blocks part of the electron beam, causing a shadow to appear at the end of the tube. Let's see if they have an actual. Okay, here you go. He's going to apply electric potential difference, very high voltage. I once got zapped by one of those, man. But I survived. Nothing bad happened to me. We're talking about high voltage here. Turn off the light so you can see the phosphorescence. Here you go. Okay, do you see the cross here? Yeah. And that's the green phosphorescence that we see whenever electrons collide with this phosphorescent material inside the tube. Research on cathode rays led to two major discoveries, the X-ray and television. That's how important it is. We ended up discovering X-rays because of the cathode ray tube, because of the Crookes tube. And the Crookes tube also gave rise to the television, to the cathode ray tube that was used in television and also in computer screens, okay? And again, here, the Maltese cross right in here, do you see the greenish color that you see here is that phosphorescent material that the electrons are colliding against and giving off that greenish color. Now, if you think about that, right now we cannot see the electrons inside the tube. We can see only the result of the collision of the electrons with the phosphorescent material, okay? But what's happening here? There are electrons moving through this space between the cathode here and the wall of that glass tube, okay? If we end up applying a magnetic field, if we put a magnet nearby it, this tube, you will be able to deflect the path of the particles, and it's possible to see that, okay, in certain experimental setups. Let's see if we can see another one. Crookes tube. Let's see if this one we can see it. Oh yeah, this one we can see it. This is a good one. Okay, so here goes. See my Crookes tube here? Let's see. Okay, yeah, this one we can see the path of the electrons. Okay. So let's play it.
We figured out that Dalton's model is not complete. And it began with this thing called the Crookes tube. Anyone's seen a Crookes tube before? This is a Crookes tube.
A nice toy to have.
The tube of black.
What did he do here? You know, he put another screen, a white screen that also has that phosphorescent substance along the path of the electrons. He put that on purpose so the electrons, you know, grazing this plate, this white plate, produce the greenish path of the electrons there, okay? Produce a greenish path. That's the phosphorescent emission by the substance that's coated on the surface of this little plate there inside.
It's mostly evacuated, most of the air is taken out.
Okay, most of the air has been taken off this tube. Okay, so the path of the electron are not interfered.
It's got an electrode on this side and an electrode on that side. If you look on the inside of it, there's a white screen, and the white screen is there for reasons I'll show you in a moment.
The white screen is there for you to visualize the path of the electrons. This white screen actually has a coating, is coated with a phosphorescent material that emits luminosity when the electrons strike it, okay?
This is a Tesla coil. Tesla coils generate lots of voltage. Right now there's a
The Tesla coil is the source for the electrons here.
Inside of here spinning, and it's got some wires around that.
The Tesla coil acts just like the high voltage source of the Crookes tube.
Magnet it's generating a lot of voltage as it spins through the strong magnet. In fact, if I hold another magnet up here, I can feel it vibrating from the spinning of the magnet. Kind of like your rumblers on your game controllers. And but this is generating a lot of electricity. You can see that if you hold it up to something metal.
Wow, do you see the sparks? Okay. There's a very strong electric field.
People always ask what will happen if you touch it. The answer is to die. Well, I am now dead. A little bit uncomfortable. But in any case, here's what happens when you hold it across a Crookes tube.
Okay. Now do you see the greenish path of the electrons? Okay. So you have a bunch of electrons traveling from this cathode to the other end, and it's leaving a track, a greenish track, okay, that you can see because of the phosphorescent material that's coated in this screen right in here. In the previous experiment, what did you saw? You saw the greenish glow only at the end of the tube, right? Because only the end of the tube had that phosphorescent material for you to visualize the electrons colliding there at that end. And then what you can do, you can apply a magnet either at the top or the bottom, and you're going to see that the path of the electrons will be bent depending on the position of the magnet and depending on the polarity of the magnet. The path of the electron is going to be bent either upwards or downwards.
Do I see that? You see it over there on that side? Anybody see it? Pretty cool. I actually can't see it from my side, but I assume you're seeing a straight green line. Mostly. I can't use this. Because I'm looking from behind. That white screen's only on the front. It's set up to be viewed from one side only. All right. Now, this is kind of interesting. Watch this.
Here you go. The magnet, right? Look. See that? The magnet is deflecting the path of the electrons according to that equation that you saw before.
Anything happen? What's happening? It's following the magnet, reacting to the magnet, it's reflecting the magnet.
Okay.
Okay.
Depending on the position of the magnet and the polarity.
That's kind of interesting.
The spacing.
I got
the beam.
One other thing to
the beam of the electrons can be bent either upwards or downward. Let's keep on watching.
compare that to. I have light here. And I'm going to pass this light to the laser light, the green laser light up here. Oh, there you go. See it? You see that? Laser light is there. What will happen to it when I get it close to the magnet? It fluctuates away because it's fluctuating away. It has no effect on the magnet. The magnet has no effect on it. So why does some light get deflected by a magnet and the other light doesn't? Why is that? What's the primary difference?
Okay, so he's asking why this green light is deflected by the magnet and the green light from the laser is not deflected by the magnet, right? Well, the answer is very simple, right? This green light here is produced by electric charges, by matter, electric charges that are traveling here. Whereas light, the green light is not the same phenomenon. The green light is not a beam of electrons, it's just a beam of electromagnetic radiation. Okay, electromagnetic radiation does not interact with the magnetic field of the magnet. That's all.
Why? The answer is, does anybody know what is different about that light from this light? Why are they different? What's one have that the other doesn't? Yes. The specific word we're looking for here. Oh, batteries are electricity. But you kind of got the right word there. Charge is the key. It turns this light isn't charged at all, it's just light. This is obviously charged because that's what magnets do, is they deflect charges. So these make things go towards them or away from them, depending on the plus or minus or the north or south pole of the magnet. And so what we have discovered here is that there's something going through here that is charged. Something's jumping out of this metal electrode into this metal electrode that is charged. And since these metal electrodes are made of atoms, then atoms must have something charged in them. And J.J. Thomson is a scientist on our paper that we researched. This is what he discovered. He discovered that these things, the atoms, had these charges inside them called electrons. Those are actually electrons going across there. And J.J. Thomson discovered them.
Okay, so do you remember the beginning of the course I told you when the electrons were discovered, right? Let's take a look there at the back. Here you go. So that's how he discovered. He discovered electrons by using this device that you see. Let's see here. We're talking about the electric charge, the electron, the proton, and the neutron, right? We mentioned that. Let's see if I have it here. When they were discovered. Oh, yeah, right here. By J.J. Thomson. J.J. Thomson discovered the electron by using the Crookes tube. Okay, he came up with this idea that what the Crookes tube had inside it was a bunch of charged particles. And as time went by, we were able also to measure the mass of this particle that is 2,000 times less than the mass of the proton and neutron, okay? That's how important this tube is, the Crookes tube is. And let's see if we go, okay, with this type of device, we can start with this type of configuration, right? Of device, we can build other type of device. Okay, let's see. Let me put some more. Okay, so I'm going to describe the Crookes tube here for you. The Crookes tube, we have two polarities, negative and positive, that we connect to a high voltage source, which can be that Tesla coil. Tesla coil can be one type of high voltage source. This high voltage source creates an electron beam and accelerate the beam between two terminals, one positive and another negative terminal. A screen with a phosphorescent substance is used to visualize the path of the electron beam. The electron beam collides against this phosphorescent substance in the screen. The screen gives out green light. Okay, and so let's write that down. The electrons graze, right? The screen with the phosphorescent substance, okay? And it gives out green light as the electron, right? As the electron graze the screen with the phosphorus, it gives out green light. That's how we end up seeing the invisible, right? The result of the interaction of the electrons with the phosphorescent substance. By approaching a magnetic bar, we observe a deflection of the beam of electrons due to the magnetic force. And now we can start talking about some important devices that we have out there. One of them is the velocity selector. This device is used in research. People launch velocity selectors in space to measure the velocity of certain charged particles that we find in space. Let's take a look here in the book. The mass. Okay, we have the mass spectrum. He goes straight to the mass spectrometer, which is unfortunate. Okay, the mass spectrometer should come after the velocity selector. Okay, so here you go. See the magnetic field. You know, we launch an electric charge in a region of magnetic field, and the path of the particle is bent. You get the same thing if you put an electric field here. That's what this is that's what this. Oh, what happened here? That's what this illustration is showing. Okay, here we have an electric field, positive charges, negative charges, two plates, right? Parallel plates producing a uniform electric field. We launch a charged particle in this field, and its path gets bent. A positive charge is attracted towards the negative of the negative plate. But you can do something similar if you put a magnetic field, uniform magnetic field between two polarities here, north and south polarity, and the charged particle is bent as well. The path of the charged particle is bent as well. Now, you can come up with an interesting device if you combine the electric and magnetic fields here, and that was the velocity selector is all about. Let's go here to here you go. Here's the Crookes tube, right? Electric fields, electron beam. Okay, the electron here, the green is the electron beam. The negative polarity of your devices here. The electric field is accelerating this electron beam. Velocity selector. Let's talk about the velocity selector. So let's start with the parallel plate configuration that produces a uniform electric field. Parallel plate configuration with electrically charged, right? That produces a uniform electric field. And then combine this electric field with a magnetic field that's perpendicular to the electric field. That's the principle of the velocity selector. Let's see how it works. Okay, so we have this positive charge placed in this field. If the charge is at rest, it's only going to be attracted towards the negative plate, right? We have only an electric field if the charge is at rest. If the charge is at rest, there is no magnetic force, but there will always be an electric force, okay? However, if we apply a velocity to this charge perpendicular to the magnetic and electric fields, something interesting is going to happen. A magnetic force is going to act on the charge, right? Here you go. Here's the magnetic force. And now, if you adjust your magnetic field in such a way to produce a magnetic force that is equal to the electric force, the net force applied to the particle is going to be zero. And the particle is going to fly through this region of electric and magnetic fields undisturbed. Okay? So that's what the velocity selector is all about. Let's write that down. Okay? The velocity selector. The velocity selector. The velocity selector is a device used to measure the velocity of a charged particle using electric and magnetic fields. Okay. So here you go. Using uniform, even better, uniform electric and magnetic fields. Okay. By appropriately choosing let's see, by choosing the relative magnitudes of the electric and B fields, it is possible to apply a net force equal to 0 to a moving charged particle. Okay. So let Q and V, let Q, V, and E be known. Okay. What should be the magnitude of B to produce magnitude? What should be the magnitude and direction of B to produce a net force of 0 on the charged particle? Okay, that would be a nice example to have for us to have. Okay, example. So here you go. Let's start it again. Here you go. We have a uniform electric field and we have a uniform magnetic field. You put a charged particle in this field, it will always feel an electric force, right? Always. If the velocity is equal to 0, it will feel an electric force. And the magnetic force is going to be 0. But if we put a velocity, if you impinge a velocity to this particle, now it will also feel a magnetic force. The question that I'm making, what must be the magnitude of B to produce a net force is equal to 0? Okay, that's what I'm asking. Okay. And again, if in a device like this one, we can put a screen, a phosphorescent screen, just like the one you saw there in the video, right? To visualize the place where this particle strikes the screen. So we can insert this beam from this point right in here in the velocity selector. And if you see a green dot, right, a green spot in this screen, exactly here, this place, you know that this particle, the path of this particle was not deflected, right? And there is a nice mathematical relation between the electric field, the magnetic field, the velocity of the particle, and the charge of the particle. Let's do that. Let's work out that the mass, right? Let Q, V, and B, E be known. What should be the magnitude and direction of the B field to produce a net force equal to 0? Equal to 0 on the charged particle. We should put there, we already have there. Okay, solution. The electric force is going to be given by, you already know that, right? From the previous chapters, QE. That was going to be the magnitude of my electric force. The magnitude of my magnetic force is going to be given by QVB, right? We want the net force to be equal to 0. Consequently, we already know that their pull is going to be contrary, right? We want for net force is equal to 0. For net force equal to 0, we must have Fe equal to Fb. Fe is QE, right? And then what we get? For net force equal to 0. Q cancels out. And let me highlight the B here because that's the parameter that we want to find. Q cancels out. And look what we get. We get this nice relationship between the E field and the magnetic field and the velocity of the particle. It does not depend on the charge. Do you notice that? It does not depend on the charge. Similarly, if you are free to adjust the magnitudes of the B and E fields, you can obtain the velocity of your charge, of your charged particle. Okay? Another example, right? Let's put it here. Another example. And by the way, you don't even have to know Q to solve this type of problem, right? Another example. Let Q B and V be known. What should be the magnitude and direction of the of the velocity vector, right? Velocity vector to produce a net force equal to 0 on the charged particle, right? Solution should be, E divided by B. E divided by B. So if you build a device, you can build a device that you can control the magnetic and electric field in the device. You can fly it in space to find out what's going to be the velocity of your charged particles that goes through the velocity selector. 1156. And here you go, velocity selector, and then we gotta start talking about the mass spectrometer. Velocity selector, okay. We did that circular trajectory, we did that. Motion of proton, here you go, we calculate this radius, right? And now we can start talking about the mass spectrometer. Let's see. Here you go, that's the red. The mass, what is the mass spectrum? The mass spectrum is a device that uses a velocity selector plus something else, okay? So velocity selector, oh yeah, right in here. That's the mass spectrometer, a new device, the mass spectrometer, okay? Just like before, we have a velocity selector. You should be familiar with that now, right? We adjust the electric and magnetic field so the net force applied to the charge, and it doesn't depend on the value of the charge, is equal to 0 in this region. And then outside this region, we put a slit to let only the charged particles that are in a given beam to pass through. And on the top of that, we add a magnetic field here. Okay, when you add a magnetic field outside, you come up with a new device that's called the mass spectrometer. Velocity selector plus a slit plus an external magnetic field. Okay. So once the charged particle exits the velocity selector, it is going to be subject to a magnetic field only. Okay, and the particle is going to happen. The particle is going to describe a circular path outside the velocity of the selector, outside the velocity selector. And then just like before, we have this phosphorescent stream to visualize the place where the charged particle impacts my screen that we have here. Okay. And once you have the place where the particle impacts the screen, you can get the radius of the circular path of the particle. And from that radius, you can find out what's going to be the charge, the ratio of the charge and charge and mass, okay? We're going to do that after the break. So here is just a qualitative idea how this thing works. Let me write down here, break from 12 noon to 12:15, okay, p.m. If you don't have any questions, let's go for our break. I'll see you in 15 minutes. Amber is here. Okay, Amber, let me get that, Amber. What's your last name, Amber? Remind me, Lopez. Yeah, Lopez. So we go. Amber Lopez, right in here. Okay. So I see you in 15 minutes. I'm back here. So let's talk about the mass spectrometer. Mass spectrometer, right? So we already know how the mass spectrometer behaves just by looking at the result that we got before when we were calculating the radius of the circular motion, of the circular path of the charged particle, right? Right in here, okay? So mass spectrometer, I want to copy and paste here. The mass spectrometer, is a device that uses the velocity selector coupled with a uniform magnetic field outside the region of electric and magnetic fields, okay? And so here you go. So we have two regions. We have two regions. One, the region with E and B, uniform E and B with uniform E and B. And I'm going to distinguish this region of uniform E and B by being that the inner, right? The region with the inner region with the magnetic field. And a second region outside the velocity vector with a uniform magnetic field that I'm going to call B out. So there is B in and B out, right? B in and B out. We do know that we do know that the velocity of the particle is going to be dependent of the of B in, right? Dependent of B in, or like that, like we calculated before, the velocity, and I have to put the B in here, right? We also know that the radius of the particle outside the velocity selector is going to be given by see, I'm putting B out here to distinguish from the magnetic field inside the velocity selector, right? Now, I'm gonna replace this velocity with this one right in here. Here you go. Electric field, so we can, would be like that, right? We do not know let's say we do not know the mass of the charge, we do not know the mass and the charge of the particle, but we know the remains, okay? The rest, mass spectrometer. So let's work that out as an example, right? Consider a mass spectrometer. You know the E and B in, right? You know the electric field, the magnetic field inside the electric field, and magnetic field inside the velocity selector, comma. And the magnetic field and the magnetic field outside the velocity selector. Find Q over the ratio of the charge and the mass of the particle. That's what we want. That's what the mass spectrometer provides us. The electric field, the magnetic field, and the two different magnetic fields can be controlled if you design your device properly, right? So solution, okay? We know that the velocity of the particle is going to be dependent on the magnetic field inside the velocity selector. We also know that the radius of the particle outside the velocity selector is going to be given by, let's see, what else? Consider, you know, E size velocity. One more thing. The radius of the particle outside the velocity selector can be measured by using a phosphorescent screen. Okay, I'm going to illustrate it here in my drawing. Okay, here you go. You put the phosphorescent screen right in here in this slit, and you keep on watching, right? Where you start to see some glowing in the screen. And let's say we already have a ruler here inscribed in this phosphorescent screen. You can measure, this distance from the slit until the point where the phosphorescent appeared, and that's going to be the diameter of the circle. Okay, it's going to be the diameter of the circle. So you do know you can find out what's the diameter. You can find out what's the radius of the circle just by observing at which point you see the phosphorescence in the screen. The radius of the particle outside the velocity can be measured. Can be determined, right? Can be determined by using a phosphorescent screen and a ruler inscribed on the screen, right? Find Q over M, the charge to mass ratio of the particle. We do know that the velocity of the particle is given by that. We do know that the radius of the particle is going to be given by something like that. And now we are left with what? We are left with this equation right here. And all we have to do is to solve for Q over M. R goes to the side, right? Becomes 1. Q goes to the left. Eliminate Q. M goes to the left. Is charge over mass. And we have this relationship here. Okay? So that's what my velocity selector provides. If you can measure the charge separately, you may be able to find the mass of the charged particle. Most likely just this type of experiment that provided us with the mass of the electron, for instance. The mass of the proton, for instance. It has to be a charged particle. Neutrons wouldn't work for this type of experiment, right? We cannot measure, won't be able to measure the mass of the neutron if we use this type of device, because there wouldn't be any electric or magnetic force applied to the neutron. So that's one important type of device. Let's see what else we have here. Here we go. We did magnetic fields, magnetic force, motion of charged particle in uniform field, velocity selector in the we did almost at least half of it, right? Okay, now we gotta look at magnetic force and the current. And let's take a look. Mass spectrometer, yeah, okay. See what he's calling this guy here as a detector, but the detector can also be a phosphorescent screen, right? Ion source, he didn't put the velocity selector here because he's just propelling the charged particle with a known velocity, okay? So he's doing a different mass spectrometer here, different drawing of the mass spectrometer. the force, and then that's going to be the next one in a magnetic field, on a current in a magnetic field. And that's something we can also observe in real life. We have a device that shows this magnetic force applied to a current, okay? So let's write that down here next. Magnetic force on a current. Okay, if moving charges feels a magnetic force, then a current carrying wire should feel a magnetic force as well. Why is that? Okay. Okay, let's see. Since a current carrying wire is nothing but several charges in motion, okay? If we subject this current, this wire, right, to a magnetic field, we should measure a magnetic force as well. Force as well, right? You get the idea? Moving charges feel a magnetic force. A current carrying wire are made of moving charges. Consequently, a wire carrying a current should feel a magnetic force, right? Here we go. Moving, I'm going to repeat, right? Repeat what I wrote in there. Moving charges can be subjected, maybe, right? May be subjected to a magnetic force. Since a current carrying wire is nothing but charges in motion, nothing but charges in motion, comma, then this wire may also be subjected to a magnetic force. Okay, just another way of saying exactly the same thing. And let's see if we have a drawing here. That's something else that I'm skipping. Let's see. Okay, right in here. Current carrying wire, right? And I'm gonna play the movie just like I played before. I'm gonna remove the current carrying wire for now. Okay, here we go. And I'm going to remove the B field here. And I'm going to put, let's see, I'm going to remove this guy right in here. No, wait a minute. Here you go. Current carrying wire subjected to a B field. Here you go. Right? So we start with the uniform B field. We label it. And next, you know what? I don't like it. Let's put more steps here. I put my current carrying wire first. There's a piece of piece of wire. Let's see, wire. Right? Current carrying wire, subject will be filled, B field. I'm labeling the B field, a wire. And in the next step, we're going to turn on the current in this wire. Now, wait a minute. First, we are going to say what's the length of this wire. Let's do like that. Length of the wire, right? And then I'm going to turn on the current on this wire. Go. And then it becomes a current carrying wire. So it is as though as positive charges are moving from the left to the right in this section of the wire, right? The direction of L is the direction of motion of the charges. If you do the L cross B, the magnetic force should be down, okay? Do you picture that? Okay, go, magnetic force. What is, magnetic force? Right here, go. Yep. Now we can start talking about the equation that allows us to find that out, right? To find out the force applied to this wire. Okay. And the way we do that is like the following. We get a very small section of the wire and calculate, get first get a very small section of a wire and calculate the magnetic force applied to this small section. It's going to be like that, okay? That small section has an amount of charge, moving charges, right? That's delta Q. Do you get the idea? And then we do something else. We do something else. We multiply. First, we multiply by delta T, right? And we also divide by delta T. A very nice trick to solve physics problems, right? Like that. Okay. Don't forget, we are talking about a very small section of the wire. V delta T is going to be the length of that small section of the wire. The length that you saw, L, okay? V, I'm gonna put it highlighted here. V delta T is going to be L, right? And I'm gonna put it highlighted as. And this one, which is going to put in red, is going to be my electric current in the wire. You see that? Let's make it theta equal to 90 degrees, right? Theta equal to 90 degrees to make the problem simpler to solve. Yeah. And what we get? We get 1 here. And we have this. You know what? Leave theta. Leave theta. So we have the most generic result here. It's better. We have the most generic result. Depending on the length of the wire. And let me put this one delta L. Let me put this one delta L here. And then, we can get the whole length of the wire, right? It's no longer going to be delta F. It's going to be F. And that's what's going to be the force applied to current carrying wire. The direction of the force is given by the right hand rule. V cross B, right? V cross B is going to be L cross B, because this L came from the V. Okay? The direction of motion of the wire, of the current, the direction of the current, by the way, direction of L in the above direction is given by the right hand rule between L and B, where L is the direction of motion, the direction of the current. Direction of the current. Okay? L is a length, but also its direction is in the direction of the current. And there is a practical application for that. If you want to understand how speakers work, you gotta look into this equation that you saw here. 21.18, figure 21.18. Let's say 10 more minutes to go, right? That's 21.18. Right in here. 21.18. Okay, we have the wires wrapped around here, the speaker. And then we have this permanent magnet with north and south pole that fits right in here in this cone, not the cone, the cylindrical portion of the speaker, right? You can see right here is the speaker. Here is the magnet. And here are the wires, current carrying wires. Okay. So how does this thing work? Here is a constant magnetic field. Constant magnetic field. And should be almost uniform here in this region. Almost uniform here in this region, okay? The magnetic field doesn't change its intensity with time. It's constant. And should be almost uniform as well. What's going to change is going to be the current that's carrying right in here. So suppose that you have a way to control the magnitude of this current. If you control the magnitude of this current, what's going to happen? This wire is going to be subject to different forces, right? So let's see. Go ahead, do the right-hand rule, right? Right-hand rule is going to be I cross B. In this case, the force is going to be to the right. Okay? And depending on the direction of the flow, if the current is flowing back and forth, this speaker is going to move back and forth as well. If you make the speaker move back and forth very fast, depending on the frequency of back and forth motion of this speaker, the speaker is going to create some different tones. Okay? That's how the speaker works. So let's write it down. Okay? the speaker, basic component of the speaker. Basic component of the speaker. Permanent magnet, a source that makes the current vary back and forth. That's what we call alternate current. Alternate current is a current that flows in one direction and back, one direction and back the other direction, back and forth, back and forth. And there are ways of doing that. We're going to cover that later on, okay? A cone coupled to a cylinder. A conducting wire wound around the cone. And I'm going to copy that drawing, so you can have it here in your notes. 6 minutes to go. The snipping tool. Yeah, here we go. Right in here. I like this picture. This is an exploded view, okay? This permanent magnet is supposed to be inserted right in here in this cylinder. So here we go. Conducting wire. In a speaker, the permanent magnet is supposed to be inserted into, let's see, in the speaker, not the permanent, the cylindrical portion of the speaker. The cylindrical portion of the speaker is supposed to be inserted in the gap of the permanent magnet, right? In the gap of the permanent magnet, like that. And then we need another picture. The other half of the picture is a very good picture, the one you have there. Here you go. Here's the magnet, right? Here's the cylinder inserted into the magnet. Four more minutes to go, okay? Cylinder inserted into the gap of the permanent magnet, okay? Current. The current in the wire. The current in the wire is controlled by a source. According to this geometry, the force applied to the wire is from the left to the right. Okay? By controlling the direction of flow of the current back and forth, comma, the whole speaker will also move back and forth. Will also, let's see, by controlling the direction of the current back and forth, the whole speaker will also move from the left to the right, okay? Depending the frequency of motion, this frequency of motion will also depend on the frequency of the current. Okay, of the frequency of the current. And if this frequency is anywhere between 20 to 20,000 hertz, you will produce a audible sound. If this frequency is between 20 hertz and 20,000 hertz, the speaker will produce an audible sound. Okay? That what we have for this one is 12:49 right now, so we are done all the way up to here, 21.5. We have more chapters here to cover, right? 1, 2, 3 sections to cover. Do you have any questions about that? It's 12:49 right now, so you can stop right in here. And I see you the day after tomorrow, right? Right now I have office hours. If you want to stay around, I'll help you out. So I see you on Wednesday.
Professor.
Okay. Hi.
Bye, Professor.
See you. Bye-bye. Thank you. Stop sharing. Stop recording.